So today we're going to look at the exponent laws. The first few slides are going to be review of things that we know, things we've seen before, multiplying, dividing, power of powers. And then we'll get into the new version or the newest exponent law we need to know. So just quickly to remind ourselves, the exponent laws, really what they are, is they're providing a structure for a mathematical shortcut or a short form. They're trying to make things faster for us or easier for us. So on their own, the exponent laws, we don't really use them very much. But as we go through our problem-solving process, we need these shortcuts which help speed things up for us quite a bit. So, going back to kind of the very beginning here, just quickly, if we had 2 to the 3 times 2 to the 5, I could write out 2 to the 3 as multiplying 3 times. I can write out 2 to the 5, 1, 2, 3, 4, 5, multiplying out 5 times. Of course, if I look at these, there's a total of 1, 2, 3, 4, 5, 6, 7, 8 2's, 2 to the 8. And then I say, what's the shortcut? If I have a 3 and a 5 and I end up with an 8, what's the shortcut? It's pretty easy to see. We know, of course, 3 plus 5 is 8. And that creates, generally speaking, that first exponent law number 1. If we're multiplying powers with the same base, we add the exponents. That's what's happening there. Same idea here with division. I can write out 2 to the 5 and 2 to the 2. We notice that with division, these 2's are going to divide out. That leaves me with 2 to the 3. Again, shortcut-wise, if I have a 5 and a 3, a 5 and a 2, how do I end up with 3? Clearly we subtract. In this case, this is the second exponent law, dividing powers with the same base, we subtract exponents. The third one, power of powers. This is 4 to the 3 squared. So 4 to the 3 squared. So that's 4 to the 3 times 4 to the 3. If I write it out, there's 3 4's there and 3 4's there. 1, 2, 3, 1, 2, 3. How many do I end up with? 6. And then, of course, what do I do with 3 and 2 to get 6? This is the third exponent law. We've seen this. This is power of powers. Again, these are all reviews, so this is not the first time we've seen them, of course, so I'm going a little quick, but we've seen these before. If I have a fraction, 2/3 cubed, I can write that out. 2/3 cubed is like anything cubed. It's just 2/3 times 2/3 times 2/3. I know how to multiply fractions. I multiply across the top and I multiply across the bottom. And what that ends up looking like is this. And then I say, what's actually happening here? And we see that really, it's that power, that 2 to the 3, 3 to the 3, has been put on each number. So if you have a fraction to an exponent, you're allowed to just attach that exponent to the top and the bottom of the fraction. That's all that's saying. If you have a product within a bracket, AB cubed is AB times AB times AB. I write it all out. I'm allowed to put the A's together. I can grab this A, and this A and put them together. And then I can grab the B's and put them together. The order that I multiply doesn't matter. We know this. If I had, for example, 2 times 4, that's 8. Or if I flipped it around and went 4 times 2, that's also 8. It's the same thing. So when I'm multiplying, I'm free to shuffle things around a little bit. I get the same answer anyway. So I have the 3 A's and the 3 B's. And again, I see what's the shortcut. If there's a 3 on the outside, I'm allowed to essentially distribute that. It's almost like distributive property. I can distribute that exponent onto the A and the B. Again, this is review. You've seen it. Now, there's kind of the second tier of exponent laws that kind of go beyond what we can see typically, but we still believe that they're true. So again, we've gone over this before. But just quickly, if I have 2 to the 3, I know it's 8, 2 to the 2, I know it's 4, 2 to the 1, I know it's 2. Now we continue this pattern. I have a base of 2 all the way down, so I'll keep my base of 2. I'm going 3, 2, 1, 0 would be next. 8, 4, and 2. How am I progressing here? Well, I'm multiplying by half. 8 times a half is 4. 4 times a half is 2. So then I must continue my pattern. 2 times a half would be 1. And this gets a little strange because you would think, kids think, 2 to the exponent 0 should be 0. Well, that's not true. 2 times 0 is 0. That's true. But 2 to the exponent 0 is not 0. Okay, it's a different thing. And it comes from this pattern. The truth is 2 to the 0 is actually equal to 1. And in general, anything to the 0. Anything. We could do this pattern with different bases. We're not going to, but if we did, we could pick any base we want. It would give us the exact same result. So anything to the 0 is equal to 1. Now, if we keep going, our base of 2 stays. Our exponent's now -1. And we say, okay, well, I had a 1. This is now a 1. What's a half of 1? Because I'm multiplying by a half every step. So a half of 1 is a half. I would have 2 to the -2. Well, what's a half of a half? That's a quarter. And 2 to the -3, that's a half times a half times a half, and so on. And we've seen this pattern before. What's happening is, this is how we learn to deal with negative exponents. If I have a negative exponent, I'm allowed to actually just write it as a fraction and turn that exponent into a positive. So if I have x to the -n, that's equal to 1 over x to the positive n. So we're going to just try a couple examples here. X to the 4 times x to the 3. I'm going to add these together. X to the 7. Y to the 4 to the 5. It's power of powers. I multiply. It's y to the 20. 3 to the -2. This is a little strange because this is saying, times 3 by itself -2 times, which we can't. That's difficult to understand. However, if I write that as a fraction, that becomes 1 over 3 to the +2. And 3 to the +2 we can work out. We know what 3 to the +2 is 9. So that's really our technique. Whenever we have a negative exponent, we have to write it as a fraction just so we can kind of understand what's going on. This one here, distributive property, this is what I want to point out because a lot of the kids do the x to the 3, they get this part right, but they forget. They got to put the 2 to the 3 as well. So that 3 has to sort of attach to the 2, and that becomes 2 times 2 times 2, which of course is 8. That's where 8x cubed comes from. Now the last tier here, the third law, and this is the sort of the new rule, has to do with fractions or rational exponents. So I want to kind of look at what we know to move into what we don't know. So I know 9 squared is 81. That's pretty easy. I know 9 to the 0 is 1, like anything to the 0 is 1. We got that one down. I know 9 to the -1 is 1 over 9. So I've been able to deal with all these so far. But the next question is, what if I had 9 to the half? What if I had a fraction up here? This is saying take 9 and multiply it by itself 1/2 times. So the language begins to break down on it. So we have to do a little conversion here, and I'll show you how it works. So just a couple statements here. Statement 1, I know 9 is 3 times 3. That's pretty straightforward. Now, I also know 3 is the square root of 9. So what I'm going to do is I'm just going to replace these 3's with square root of 9. Okay, that's statement 1. Statement 2, I can say 9 to the 1 is, well, 9 to the something times 9 to the something, using my exponent laws. Okay. By that first exponent law, I know I have to add the exponents to get 1. Multiplying powers for the same base, add the exponents. So I know a plus a has to equal 1. So 2a would equal 1, a has to be a half. A half plus a half equals 1. So I now know that 9 to the 1 is also equal to 9 to the half times 9 to the half. And what we can notice from this is actually the square root of 9 is exactly the same as 9 to the half. So we're going to link these fraction exponents, which are really kind of weird to understand, into roots or radicals, which we're familiar with, which we can understand. So what this is saying is that, and you can try this in a calculator actually, if I have a root 9 to the 1/2, technically that can be written as a square root of 9 all to the 1. And we see that, how we can link these together. The bottom number of our fraction is the radical, the root part, and the top number is just the power. So let me just show an example of this, and the base stays the same, of course. Let me show you an example, and you can use your calculator on it, and we'll see it. Okay, if we have, for us to deal with rational exponents, we have to convert it into radical form. We have to put it into root form. So what this is saying is that if I have x to the a over b, that's equal to the bth root of x all to the a. That's how I get my answer. So for example, suppose I have 16 to the 3 over 2. You can try on your calculator if you want. If you want to, on your calculator, type in 16, up, or y to the x. You can put 3 over 2. You can put in 1.5. It's the same thing. and see what you get on your calculator. So for us to convert it, I know that my base 16 stays the same. So the base of 16, my base of 16. This bottom number in my fraction becomes what root I'm looking for, and the top number just stays as the power. So now this is saying, well, basically it says 16 to the 3 over 2, that's equal to the square root of 16 cubed. So the right-hand side is much easier for us to deal with, because I know the square root of 16, that's obviously 4. Okay, they move over. Square root of 16 is 4, and 4 cubed is 64. So the same thing, if you use your calculator and you type in 16 to the 3 over 2, you should get 64 on your calculator. And that's what it's doing. Your calculator is actually just square rooting it first and then putting it up to the power of 3. Okay. Similar idea here. 27 to the 2/3 is tricky for us to understand. However, if I convert this into radical form so I can see it, this is just saying, okay, the 3, the bottom number becomes the root, and the top number stays the power. So this is saying the third root of 27. I need a number I multiply by itself 3 times to get 27. Okay, I could try some numbers. I could try 1. 1 times 1 times 1 is 1. No. I could try 2. 2 times 2 times 2 is 8. No. I could try 3. 3 times 3 times 3, yes, is 27. So I know the third root of 27 is 3. And then 3 squared, of course, is 9. So for us, we can see some other type of numerical roots. Square root of 9 is 3. The third root of 8 is 2. Okay, this is saying what number do you multiply by itself 3 times to get 8? Okay. We can have higher roots, of course. The fifth root of 32, a number that we multiply by itself 5 times to get 32. That would actually be 2, because 2 times 2, 3, 4, 5. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So the fifth root of 32 is 2. And the last one here, third root. And I want to point this out too, because we're so used to seeing, square root of whatever, -9, okay, does not exist because we can't have a negative square root, and that's true. But we can have a cubed root of a negative number. Okay, so we don't automatically just ignore this. We can actually work this out. Okay, that would actually be -3. Let's try it. So -3 times -3 times -3. So -3 times -3 is 9. And 9 times -3 is -27. Okay, that's it. Try page 175.